So I would like to thank Syzygies for bringing us here. It's a wonderful place, and yes. So, direct image complexes. So I'm reporting basically on the paper with David Eisenbud some years ago. The paper isn't cited very much, and I think it should be used more because it's a fundamental tool to compute things. Now, direct image complexes, maybe I start with an anecdote. When I was writing my PhD thesis under the guidance of David Eisenbud, at a certain point it was obvious that one should use a direct image construction, pi lower star of something. And well, I didn't know about pi lower star. I mean, this is chapter 3 of Hartshorne. Most people are, at the time of their PhD, are still a little bit scared about parts of Hartshorne's book. So I worked around it, and David didn't correct me. He was fresh in algebraic geometry at that time. So I actually figure, I don't know whether it's true, that neither he nor I would know what the direct image complex is. So it's very nice that we came back to this. All right, so Tate resolution. The Tate resolution of a coherent sheaf F on Pn is a double infinite free complex over the exterior algebra which encodes the cohomology of F. Applications include the Beilinson monad, Schau forms and resultant, Boy-Söderberg theory, and the direct image complex in the local or affine case. So I was lucky that you already had an introduction to Tate resolution. So I will start out with applications of direct image complexes to convince you that this is something we should know how to compute. And then review Tate resolution on projective space. Then I go to the relative setting in affine local base. And then I illustrate this on vector bundles, deformations of vector bundles. Point P1, that's the plan. And the last section will be, for today, direct image complexes. The question, are they special? So, A in the Noetherian ring, F a coherent sheaf on projective space over A. So this is Pn cross spec A. Pi is a projection to spec A. Then if we have a sheaf, a coherent sheaf on Pna, we form R pi lower star of F. So what is this object? Well, this is if A M K is local, so M is a maximal ideal, K is a residue class field, is local, F flat over A, so I will restrict myself to flat case, so these techniques which we have work more generally. Then this R pi lower star of S, first of all, is a bounded complex of A module, and it's actually represented by a minimal complex, A to the H0, A to the H1, up A to the Hn, for some numbers Hi. Minimal in the sense that the entries of these matrices are in the maximal ideal. So it's given by a bunch of matrices. And it's unique up to isomorphism. The formation of this complex, that's the most important thing, commutes with base change. For example, I could do base change to spec K. Then this complex would compute the cohomology of Hi of F tensor K, so the restriction to the special fiber, which then tells me that the Hi here are just the dimension of these groups. So in the situation where I will be in, I will have good information about the special fiber. I will know what these numbers Hi are. And the task would be to actually compute the matrices which gives this. See, John, you look puzzled. All right, so the task is to compute these matrices. But first, let's see.
All 5 they are same. All 5 they are same. For all fibers they are same.
No. This is so the HI is a special fiber over the origin, over spec K, right? But then the neighbor ring fiber might have different cohomology.
But if it's flat, then it's not.
No, it's not. I'll explain that in a second in an example. Okay, so let's do one of the favorite examples. In curve theory, we look at the Poincare bundle on C cross pic D, the projection to pic D, and then we have the Bernoulli loci. L is WRD. This is a line bundle of a degree D, which has at least R plus 1 sections. And I want to take a line bundle which has precisely R plus 1 section, so it's not contained in W R plus 1 D over C. Then, to get into the local situation, I look at the local ring of the Picard variety at the point L. I restrict my Poincare bundle on A, so this is now living on C cross spec A. And then I can push down this restricted bundle. And of course, I only have 2 terms because if C is one-dimensional, so I have an H0 and H1 of L. And I get these complex A to the H0 of L, A to the H1 of L. And the entries here are in the maximal ideal of this local ring. So H0 of L is by assumption R plus 1, and H1 of L is then by Riemann-Roch G plus R minus D. So this is so we know the size of the matrix, and now if we now ask which nearby L's, I also could take an affine neighborhood if you want. Right. The nearby L's, which of them still lie in WRDC? These are those where if I plug in the value, the matrix is still the 0 matrix. So I have H0 times H1 many entries of this matrix. So the codimension is at most H0 times H1. Right? So, the Torelli theorem. So now I take L in W1G minus 1C, which sits inside W0G minus 1C, which, as you all know, is isomorphic to the theta divisor, which is the lambda invariant divisor on CG defined by the Riemann theta function. Right? I would like to expand the Riemann theta function in linear coordinates on CG, or to be fancy, I have this group structure CG plus, which is the group structure on the tangent space of the Picard variety, and I take the exponential map to the Picard variety translated at the point L. So 0 goes to L. And since I have 1, H0 is going to be 2, and H1 is going to be 2 as well. So it will be a square matrix because I have here look at bundles of degree G minus 1. And so the theta function, so this is the matrix which goes from A2 to A2, will have is a 2 by 2 matrix. It vanishes at the origin. So if I expand this in homogeneous form, then I have a linear form, quadratic form plus higher terms. Right? And to say that my bundle nearby stays in W0 G minus 1, means it still has a section, which means that still that the rank of this matrix should be not full. So it's theta x is defined by the determinant of this equation. So we have theta 2, which is a quadric, theta 3 plus higher order terms. Now, consider the tangent cone of W0 G minus 1 at C. So this is defined by the leading term, theta 2 equal to 0, which sits inside PG minus 1. I can look at this projectively. And I also look at the oscillating cone, which is defined by theta 2 equal theta 3 equal 0. So these are lines through the origin in CG, which sort of touch the theta divisor at least to order 3, right? The tangent to order 3 to the theta divisor. So well, theta 2 is just the rank 4 quadric defined by the Lij's. So this is, unless a special situation, is going to be P1 cross P1, and its T will be a cone with vertex set defined by L1 up to L22 in PG minus 1. So it's a cone over P1 cross P1. And the most natural thing to study this is, of course, to blow up the vertex, and then this becomes a PG minus 1 bundle. So I blow up PG minus 1 at the vertex, then it's a PG minus 4 bundle over P3. And the tangent cone blown up is a PG minus bundle over P1 cross P1. Now what about the quadric bundle? First, if you look at the expansion here, you see that the vertex is contained in the 0 set of the cubic, because the cubic terms involve, each cubic term involves an Lij. So if I blow up the vertex, the vertex is going to be a divisor inside the blown up oscillating cone. And well, it's a cubic, and I project from a point or for a linear subspace of a cubic. If you project from a linear subspace of a cubic, so I take a point down here and maybe a line lying over it, then I already know one point, the point on the exceptional divisor, and there are 2 points left. So this is going to be a quadric bundle, right? And so here is an old result of Mein and Kempf. If C and L is general, we can be more precise about what we need, then the discriminant of this quadric bundle, D, is the image in P1 corresponding to 1 under the map of C under the map given L cross K minus L. So this, I think, is a very beautiful result. It tells you that if you are in the quadratic singularity of the theta divisor, and you know the expansion of the theta function up to third order, you can recover the curve plus the line bundle up to symmetry. So I would like to make a cartoon about this. So I have P1 cross P1. Right? And in there I have my curve. Right? And for a given point here, I have a whole P3 mapping to that point. So this is going to be a P3. genus is 7, so G minus 4 is the P3. And inside the P3, I'm going to have a quadric. Right? Now this is for a point not on the discriminant. So it's not on. But if I move to a point on the discriminant, then I'm going to have a quadric cone. And actually this point is in C. The singular point will be a point of C. And if if I move from this side to that side, so I'll take maybe a point in here. This is now going to be, of course, a two-sheeted hyperbola, right? The other type. So if you move from here to here, it changes, right? And now, if you are in the even more special points, a double point, then how does a double point picture look like? Well, then we have a pair of planes. And somewhere in this plane there will be 2 points which I don't see. I would see them if I go nearby, right? I would sort of find this, right? So that's the picture. This is a cartoon. One of the things which I try to convince my students to do for me is to compute this. I want to replace this cartoon by a real movie. It would be rather nice. Right, I have a screen downstairs where I can move my point with the finger, and then these fibers would move, right? And I would really like to see what happened, right? That would be nice, right? So one of the ingredients is to compute this matrix, which is the direct image complex, and I'm going to tell you how this works. The other ingredient, which was this exponential map. You have to do the deformations right. I mean, analytically, the theta divisor is at that point is isomorphic to the cone. I mean, L11 plus. I mean, this entry is a local coordinate, right? Locally, analytically, the cone is the theta divisor is isomorphic to its tangent cone. So it's really very important that we choose these group coordinates. So in this Torelli theorem, we use the group structure. We use this group structure at the given point up to second order, right? But not more. All right, so I try to convince my students to do that. It involves, of course, also a lot of programming. And some do like and some don't like programming, and I picked the wrong student. Maybe somebody else will help me out. So I'm going to review Tate resolution on projective space. So K is the ground field, W an n+1 dimensional vector space, S is symmetric algebra on W, so this is a polynomial ring with coordinates say x0 up to xn, so a homogeneous coordinate ring of Pn. I take V, the dual of W with dual basis E0 up to En in E, the exterior algebra. Or same as in Hausdorff. So the causal complex proves that the exterior algebra is the X algebra over S, kk, and similar that the symmetric algebra is the X algebra of E, kk. So E is, except for being not commutative, E is a very nice ring. It's Gorenstein with dualizing module omega E hom of k e to k. I mean, this is finite dimensional. So if anything has a chance to be the dualizing module, then it's this, right? And so it's, and of course that's lambda w. So this is a free module, which is sort of something which is behind the whole theory. So E is, for a homological point of view, much better behaved because injective objects are the same as projective objects. So it's easy to compute injective resolutions over E. Then we had the BGG functors, so M a graded module. Hal wrote this down with a tensor product with omega E, which you certainly can do. Here is sort of if you do this with hom, then so a homomorphism phi is sent to the homomorphism which sends E to phi applied to E times EI times XI, which then, so this here ends up in MD, a multiplication with XI ends up in MD plus 1. Similar for graded E module, we have these kind of complexes, L of P, and well, one thing is to remember that they choose the degree of EI to be negative, so EI times P has lower degree than the original one, so that makes sense. So it maps from P0 to P minus 1, and so on. So we have these two functors, R, which takes graded module to linear complexes on L, and they extend to a pair of adjoint functors, L and R, from complexes over S to complexes over E. And the fundamental theorem of Bernstein-Galfand from 1978 is that the derived category of S and the derived category of E is the same, or the derived category of coherent sheaf on Pn is a stable module category. We saw in Hal's talk that if we take E, the free P module, and apply L of P, we're going to get the causal complex, which resolves the residue class field. But if we sheafify this is going to be an exact complex. So exact complex, of course, is a trivial element inside DB. And so anything which factors over a free complex will be sort of a zero map. So that's why we get the stable module category. So this is a category has the same objects as the module category over E, but the morphisms are all the morphisms except modulo those morphisms which factor over a free one. All right, so this now the Tate resolutions. No, I'm going back. I can't do this. I wasn't done with the Tate resolution. So M a graded module, F the coherent sheaf, and R at least the regularity of M. Then this module is cyclic. So Hal explained that last time. And actually we have a very nice result. So if M is an S module and P an E module, then P to RM is an injective resolution if and only if L of P to M is a projective resolution. So there's that's a nice statement, I think. Looks nice, at least. Now, coming to the Tate resolution, as Hal explained, we're now going to replace P by its projective resolution. So this will be a projective resolution. It will be infinite. So it's going to be a double infinite complex. Right? I mean, certainly there are terms out here, because if M is not the trivial sheaf, there are sections in a large degree. So MR plus 1 must be non-zero. On the other hand, I mean, graded resolution of the X-here algebra cannot stop because of the grading. I mean, yes. So this will be an infinite complex, and then as a result with Gunnar is that the terms of this Tate resolution encode the cohomology. So I removed from the Hom version to the omega E version. I put in here an I minus D because I can't decide whether I regard this as a vector space or a vector space in a specific degree. It's better to regard this as a vector space in a specific degree. Here in this notation, I didn't do that. All right? So any of the cohomology groups occurs in a precise position, and you see here are these sliding indices from Castelnuovo-Mumford regularity, so this fits very well. Okay. So relative Tate resolution. So now I'm going to replace the polynomial rings by polynomial rings with coefficients in A, and there's a typo. And the axial algebra is the axial algebra over free module of rank n plus 1 over A. F is sheaf on P and A, and M greater equal to R, the module of global sections. So we can form R M greater equal to R. So this is an exact sequence of free EA modules. So this is no longer finite dimensional vector spaces, but these are going to free EA modules. And the Tate resolution is obtained the same way as before. We have this free module, we have a kernel, and then now we resolve. And we can tell if we know the special fiber, if we know the fiber over the origin. So A was a local ring, remember? So this is a cohomology, it's a special fiber. Then we do know the Betti numbers of this FD. So this is going to be a sequence of free EA modules. The differentials, however, now can have maps of degree 0 in the EA, in the EI variables inside EA. So if I just write down the terms, maybe I call them n, then I will sort of, here it's linear, but then we could have sort of terms in larger degree. So, and these are the terms which sit on the diagonal. The E differential goes to the linear, and E goes in this direction, quadratic, and E goes from here to here, for example, right? This map would be of degree n. But there could be maps here, which are of degree 0 in the EI variables, but have entries in A. And the claim is, if we take the Tate resolution and kill the EI variables, so this, of course, is just A, then this is the direct sum of all the direct image complexes of the various twists. So, of course, I don't have to compute the whole Tate resolution if I only care about this piece. I have to go up to the regularity, form this matrix, resolve backwards, and look at this strand here. So let's do a very simple example which you all understand. So I'm going to deform the vector bundle O of minus 2 plus O on P1. The infinitesimal deformation are parameterized by x1 of EE, which in this case is one copy of K, and they correspond to an extension O to O minus 2F. If I choose a non-trivial extension, it's clear what it is. It's going to be 2 copies of O minus 1, right? But if I choose the trivial extension, then of course it will stay. So the Betti numbers here are the Betti numbers of the special fibers. So in degree 0, I have one section, and H1 is O of minus H1 of O of minus 2 is also 1, so we here have a 1. Then if I twist up, then this has no sections, and this has 2. But if I go here, then this gets 1 section here, and that gets 3. So we have 1, 2, and then sort of it grows up by 2 all the time, and the other way similar, right? And it's sort of, So this actually lives not only over infinitesimally, but it really lives on P1 cross A1 because the X2 group vanishes, so we can have no abstraction whatsoever. So the Bettinger diagram is as I told you. Now, it's easy to guess what this 1 by 1 matrix looks like, right? This should depend on my variable A. So I guess this should be A, the matrix with only one entry. But let's compute this. So H0 of f in degree greater or equal to 2 is globally generated by sections. Well, I get one section which comes from the term there, and then two, and then three sections there. So 1 x square, xy, y square are sections. Of course, x square, y square, x square, xy, and y square are lifts from the section in the on the right-hand side of the extension to the middle. And what is the presentation? Well, of course, the presentation, this here is just a presentation matrix of these sections. But since I lifted, if I take a linear combination of these two, they no longer are 0, if I take this relation, but be a section in the second component. For example, it could be that this linear combination is minus ax, and the other one is 0. You see that here is a certain amount of choices. So this is a presentation matrix, but the presentation matrix are not unique. I can change bases. For example, I can change add this column to that column, the a times. So I could move this minus ax to ay here, right? Certainly, if I look at this extension, what kind of extension do I have? Well, I can use these two y's to remove all the y's. I can use these x to remove x here, so there will be no entries here, and all I have is sort of one choice here. But I can do a different choice. I can prefer the x's before the y. So now at the basis of H0 of F3, we have the elements, well, we have these sections. I can x times 1, y times 1, and then x times x square, and so on. And so we see from the relation, if I multiply y times xy, y times xy, that's going to be the same as x times y square. X times y square. However, if I take y times x square, this is not quite the same as x times xy, because I have this term here. It's going to be a times x times 1, right? So I just repeated what I saw. Y times xy is xy squared, and y times x squared is x times xy plus a x times 1. So I form this matrix. I see that 1 is going to be mapped to x times 1, y times 1 with coefficient EF. I'm using sort of coordinates x and y in E and F, instead of x0, x1, and E0, E1. Then here I get an F term because x times xy is the same as, this is, what do I do? It's, x times, I multiply this x square terms by this element x e plus y f, right? So if I multiply that, I'm getting to get an x times x square term with the e coefficient. Then I get an x square y times x squared coefficient term, which is an x times xy. So here I get an f, and here I get an a times f from that a. And, well, the other one. So that is my matrix, one of the differentials in the Tate resolution. And now I can resolve backwards, so I can compute the kernel. So E times F annihilates this column. So I have this relation. AF, EF, 0 is a relation of all the columns, so it cancels this one. Here I get E times AF plus A times FE. So since E and F anti-commute, this is 0. A times F square. Then I have E square, EF, and F square. So the second column is a relation, and this is a relation as well. So of course it's only matters down here. Right, this times that multiplies to 0. So that is phi 1. The next kernel, what can we do? Well, I claim that A, E, F is a relation. So A times EF plus A, FE, that's 0. E times E is 0. F times E plus E times F is going to 0. And F square is going to 0. So this is a relation. And E certainly is also a relation. So E multiplies this to 0. And there are no further terms. And F multiplies this to 0. So there are no further terms. And it has the right size of matrix. So there are no further relations. And then this matrix pretty much is symmetric. So since the Tate resolution, if I dualize it, will still be exact because I'm dualizing the free module is an injective module, so I can dualize. It stays exact. So it will be basically the same matrix as this, except that the order of the products has to be changed. This comes from the fact that we have to distinguish left and right modules, and if we want to move from a left module to a right module, then we should use the opposite order of the multiplications. So this is not. So here's a more involved example. I take a rank 3 vector bundle globally generated of degree 6. The most special bundle of this type is O of 2 plus O of 6. 2 copies of O plus O of 6. And the extension space this times is a 10, 10 being 2 times 5. I can compute the Betty numbers of the Tate resolution of E. They look like this. So of course I have in degree 0, I have 2 plus 7 section, which is 9. But then, and there's no H1 here. If I go down one step, I lose the 2 sections there. And from the 7 sections, 6 survive. So this will be 6. And there's still no H1. But then if I go down, so this goes now slowly down from the OP1 of 6, and well, this will be 2 sections, and then it goes up with 2, finally to the point where it goes up to 15. So that's the Betty table. And we have I've only written down the matrices which are on the diagonal. So there's a 1 by 10 matrix, a 2 by 8, 3 by 6, 4 by 4, 5 by 2 matrix. The 1 by 10 matrix, you have 10 entries there, all they are. If I deform it all, this is going to go away. And then you have these nice pattern. So this, this sort of is sort of a rational normal curve. But there's a sort of a second version of rational normal curve in the second set of variables. Then you sort of have this term, which is a 3 by 6 matrix. Then we have the square matrix, B4. And then we have B5, which is a sort of the last matrix. So what is this? So stratification by rank conditions. So Ri is the rank of Bi at the specific point. If R1 is equal to 0, it has rank 0, so it's a 0 matrix, then we haven't deformed anything, we are at the origin. Now, to get splitting type 510, this is characterized by the fact that this map must have a kernel, because there should be an the O5 should have a section here. So has a kernel, so that we have the 5, and the remaining part has sort of to add up to this. Then this here, which is split in type 520, is characterized by the rank of R3 is not full, so it's less than 3, so we get one section here. But then we also need a condition that R5 is has rank less than 2 to keep a co-kernel here to have that 0. All right, and so on. So you have these nice stratification by ranks, and yes.
Just go back to the slides.
Yes. And? So this is a stratification, and this is a geometry. So here was R2. Let's see what R2 was. R2 was this matrix, and the 2 by 2 minors of this matrix define a scroll of type 4, 4. So this is S4, 4. So this is S4, 4. And then the situation is, so this is really P1 embedded into P4 in the 4 upper embedding cross P1. This is S4, 4, right? Within the Siegel product of P1 cross P4. So this stratum is a secant variety within this P4 cross P1. And then we have a stratum which looks like P4 cross P1. We also have a stratum which is the secant variety of S44 itself. The determinant is the 3 secant variety of S44. So can we see that? Let's see. So this is a square matrix. And so S44 is defined by the 2 by 2 minors of this matrix, right? All the 2 by 2 minors which occur here also occur here. So to say that the matrix has not full rank means that we can have 2 points, a span of 2 points inside this variety. I mean, it has rank 1 in S44, and then having rank 2 means I'm I'm slightly confused myself. Having rank 2 means being in the secant variety, and having rank 3, which is not full rank, means that we're in the 3 secant variety of this thing. All right, and these are the codimension degrees. So this is one example. Of course, we can deform any bundle on projective space and see how this stratification looks like. We believe that the rank conditions, the various rank conditions which we can put, always define radical ideals. It's true in this case, but we don't know whether it's true in all cases. So let's come to the last question: are direct image complexes special? So the answer is, well, if there would be special, Grothendieck would have told us. So they're not special. So every bounded minimal free complex of a local Noetherian ring is a direct image complex. So let's see how this goes. By flat base change, it suffices to prove this for the generic complex. So I have a B, the polynomial ring with entries, all the variables in the matrices. And the relation I have to put is that this is a complex. The piece map composed with the p+1 maps is going to be 0, so lots of quadratic relation. So spec B is known under the name variety of complexes. It describes the complexes with these given Betti numbers. So we first show that B is a base basis of Wessel deformation of a bundle F. Deformation F of the vector bundle F0. I take the omega I, so I take omega Pn Z over Z, so this is a relative cotangent bundle, and take the lambda i's product, and I take this bundle, I take that many copies, BP copies of that, and I'm going to try to compute the versal deformation of that first. So certainly I have to compute what the x omega p omega q are, and it turns out they are sort of the x1 is going to be the h1 of omega 1, which is z, if and only if q is equal to p+1. Right? I mean, this is z, and this equality holds only if q is p+1, and 0 otherwise. And the h2 groups are similar, so in this case q should be p+2. And yeah. So the tangent space of the versal deformation is the direct sum of the Hom spaces. Right? And the abstraction space is the direct sum of the consecutive Hom spaces. With the abstraction map, I have a sequence of matrices maps to all the compositions. Right? So the base space of this B of this deformation is the coordinate ring of the variety of complexes of free modules of rank B0 up to Bn. So now we have our object. Now it's supposed to compute. So F on P and B denotes the versal family. We compute in terms the terms of the Tate resolution TF, which are uniquely determined because B is a graded ring. So it's clearly a graded ring, so it's as good as a local ring, so they're unique up to isomorphism. And all right. So I claim that the Betti table looks like this. It has sort of some numbers, non-zero terms in degree 0, in strand 0, and then of course there's some Hn cohomology, and there's only one diagonal, one term in the middle, and it will be beta 0, beta 1 up to beta n. So there's one diagonal. So why is this? Well, the Tate resolution of the omega p has a 1 here, and then so in this column there's only one term. There's a 1 here, they're all 0 here, all 0 here. The middle cohomology all vanishes altogether, and there's only one map here and one map here, which goes in and out. And this here, So this is in position P. This is given by all forms of degree P plus 1. And this map here is given by all forms of degree n plus 1 minus P. Right? So if I wedge these forms together, I get the forms of degree n plus 2, which are automatically 0. So this clearly is a complex, right? I mean this, and then it continues. So this, I have a bunch of those, and they contribute sort of to the beta P here. And well, of all of them, and I add them up, then I get precisely those terms on the diagonal. So now we have to compute the relevant maps. We want to prove that the map on the diagonal of the which goes from hom EB beta B beta to this term. So this is one of the terms of the piece differential, is given by the matrix AIJP. And we make base change. We do this after base change. We just kill all the variables which are in the different matrices. So if you make that base change, then we get a bundle G plus the terms which are no longer deformed, which is sort of the sum of all Q, which Q is different from P and P plus 1 omega Q to the beta Q times BP. There is a typo. So this reduces the claim for a two-term complex in a compilation of only two non-trivial differentials in T of E. So let's do that. So I focus on these differentials from TP to TP plus TP minus 1 to TP to TP plus 1, and only one entry. I had a direct sum, so only one entry. So the terms were at an omega E here. I'm mainly interested in this map. And I do know this map here. This is from one of the summands and the up there and the other summands. So the matrix D has a term D1 is 0, which is sort of, there's no maps from here to here, but there's a map here, here, and here. And C similar, there's sort of a map going up, but nothing down, which comes from the fact that they have a certain direction. So, so we have to determine the entries of C12, which are linear in the C EIs, right? This sort of changes the degree by 1. They are linear in the EIs, linear matrices in the EIs. Now, if I go this way around, this, and up, I have matrices which are in E0 up to the En, n plus 1 minus P times. Actually, all the entries, right? Because from here to here, this is of degree n plus 1 minus P difference in degree. So I get that. On the other hand, if I go from here to here, I get stuff which is of degree n minus P. So, but this here is a larger power. So this is contained in here, and I can solve uniquely for matrix C12, which goes here. So which sort of produces two terms in the complex, and it extends to the whole Tate resolution. So this proves that I get the right entry at the right spot, and this extends to versal deformation of G prime of omega P, direct sum omega P plus 1, and we get the result. So the generic complex F of the coordinate B of the variety of complexes is the direct image of the versal deformation F of the vector bundle F0, which was this direct sum of line bundles. So I think I stop here. Thank you.